fossil records, after the Cambrian expansion, we know that there are 5 mass extinctions, and this is the first one, caused 60% of marine invertebrate died, and the third one is the largest one, and the last one caused dinosaur extinction and lead to the dominance of the mammals. And so after that, we still have biodiversity work, so we can act. So there are two different situations, biodiversity and extinction. So we can ask ourselves, do we have model to model this system so that we can describe the population dynamics and also predict some ecological stability from the basic interactions. And evolutionary game theory provides us a tool to investigate this kind of dynamics. And we start from the payoff matrix, and then we can write down the witness, and then we can write down replicator equation, which describe the dynamics between different species. And but however, in this framework, we don't know what does the finite population and the spatial network could lead to different results. So what can we do is by the numerical simulation, we put individual and set some game rule and introduce randomness, so we can study the evolution of ecological system. And so that's our system. We just focus on the rock, paper, scissors game, and the payoff matrix is on the left, and on the right, the usual, we have the tie game, the -1 and 1, but we can change it to some other value. So this one, the +G, is how we use in the following investigation. So the accuracy in this game provides us an opportunity to investigate the biodiversity. And some basic on this system is, if we do numerical simulation, we will have 3 different type of scaling form of extinction time. And if for the neutral one, the center, we have some power law. But however, if the ecosystems are unstable, we have the log. And if the ecosystem is stable, we have the exponential form. And if we put the system on spatial gaps, that means we restrict the individual, the red one, to interact with its neighbors, only the 4 nearby him. And it's an interesting concept come up because the interaction is local, but the global, the dynamics and the stability are global. So we can ask a question: do we have a payoff matrix to describe the global ecological stability, the global dynamics, not the local one? And so first, we just see the extinction. As we said, different extinction function means different stability. So different from the well-mixed case, in 2-dimensional networks, we all have exponential form. So it implies that the ecological system are ecological stable in 2 dimensions. But we would like to know why. So from the animation, we know there are 4 stages: the initial and the steady state and the pre-extinction and finally there are no green ones. So this is what we call extinction. And we found that system spend a lot of time in this state, and animation shows some broken spiral wave. So we would like to know, is the broken spiral wave correlated with the biodiversity? So I will skip this page. Yeah. So we just look at the temporal correlation time. Different different from the well-mixed case. The well-mixed case, the temporal correlation decay right away, and there is no oscillation, so we can know that the correlation time is quite short compared to the two-dimensional case. And another is the spatial correlation, but the spatial correlation in two dimensions is an exponential decay, so it's a short correlation length compared to the system size, which implies that there are no pattern formation in the system. So which echoes to the broken spiral wave I mentioned before. And this spatial correlation means that system only synchronize locally, not globally. Because if we have longer correlation lengths, that means the system are synchronized, or you can say coherent as a whole, and so we can expect that the dynamics is different. The dynamics in local is different from that in global. So that echoes what we like to know, the global payoff matrix. What does the global payoff matrix look like? And from the correlation, we propose a possible mechanism for the biodiversity. And this is a larger system, and you can see sort of broken spiral wave. And so ecological system can be divided into several units, and each unit has a, you can imagine, has a source which can generate biodiversity, but unfortunately it cannot spread out because the destructive interference. So we will see the broken spiral wave, and after that we can see that's what we want to do. The color is not clear, and this is the final result we have. And because for the well-mixed case, we have no renormalization on the payoff, so it gives us a gray line, red dashed line. But however, on the two-dimensional case, the curve change. It becomes quite flat. So, and in this regime, it's not clear to see. In this regime, should be ecological stable. So, but however, for the G larger than 1 here, the stability seems to suppress. So this part we don't know why, and maybe we will do some research on this. And also we show some finite size correction on the small G region. Also, this is all what I done. We provide a mathematical tool to investigate the payoff matrix in spatial games. So we can apply it to different systems or different networks to get the global payoff matrix to describe the population dynamics. So yeah, thanks for your attention.
Okay, thanks.